On Friday, we established that a connection between electricity and magnetism, and that connection is pretty simple, actually. In 1819, Hans Christian Ørsted discovered that electricity generates magnetism. Electricity produces magnetism. And by electricity, what do we mean? Well, moving charges. If you have an electron that's moving through a wire, or an electron that's moving through the air, or an alpha particle that's moving through the air, any charged particle that's moving will generate a magnetic field. Now, there is a kind of a complement to that as well that we'll talk about in the next few days, but for now we'll just focus on that part of it, the whole idea that electricity generates magnetism. Now, that magnetic field has a very specific, predictable, defined shape. What is the shape of that magnetic field? If I was to draw an electric current, let's say an alpha particle, let's say this time, so positive particle, going which way? That X tells me it's going which way? It's going into the page. If I've got an alpha particle going into the page, what's the shape of the magnetic field surrounding this moving alpha particle? Circle, yeah. In fact, it's a series of concentric circles, right? Here's one circle, here's another one. What do you notice about the spacing of those circles? As we get further and further away from the alpha particle that's causing the magnetic field, the field lines get further apart from each other. Not just further away from the alpha particle, but further apart from each other. And that tells us what about the strength of the field as we get further away from the alpha particle? It weakens, yeah. The density of the field lines, you guys learned this last year in Physics 20 in the context of gravitational fields. And even last unit, in the context of electric fields, the density of the field lines represents the field strength. So the closer they are together, the stronger the field, the further they're apart, the weaker the field. Clearly, the field should be weaker out here than it is right here. When you're further away from what causes it, the field is going to be weaker. All right, what about the direction of this field? Considering that it is a vector field, magnetic field has a direction associated with it. What's the direction going to be? Well, for this, we're going to use what we call the wire grasp rule. Left-hand wire grasp rule for a negative particle and right-hand wire grasp rule for a positive particle. So this is an alpha particle. Everybody take the right hand here. Good idea, by the way, when you see a question, draw attention to what type of particle it is, because it's so easy just with a silly little dumb mistake to mix up the hands and use the left hand when you should be using the right hand, or the right hand when you should be using the left hand. This is an alpha particle. This is a right hand question because it's a positive particle. So take your right hand. Everybody do this, please. Everybody take your right hand and stick your thumb in the direction that the particle is moving. Now, you can do this in the context of my page or in the context of your page. It doesn't really matter. Okay, if it's mine, your thumb's going to go like this. If it's yours, your thumb's going to go like this. Doesn't really matter. You're going to get the same answer either way. If I stick my thumb in the direction of the moving charge and I bend my fingers, then my fingertips, my fingernails will point in the direction of the magnetic field. So I'm going to say thumb in the direction of that particle, fingers in the direction of that magnetic field. Right now my fingers are above this moving charge. So which way are they pointing when they're above the moving charge? Dawson, which way are they pointing right now? To the right. We'd say the magnetic field there above it is to the right. What about right now? Shaylin, what about right now? Which way are my fingers pointing? Pointing down. So when they're to the right of it, they're pointing downward. You can see it doesn't matter how much I clench my fingers, okay, because my fingertips are still going to point clockwise here. It doesn't matter where I put them, whether I put them up above it or to the right or below it or whatever. Okay, in the end, no matter how much I clench my fist or wrist and how much I bend my fingers and where I put my fingers will point clockwise in the direction of the magnetic field here. So I can do it this, whatever, or I can just do it once and then just continue the loop around like this. Does that make sense? Now we had some questions that were a little bit more challenging as well. Questions like this where maybe an electron was moving to the right through a wire. And we wanted to find the magnetic field strength above this wire, below this wire, in front of this wire, and behind this wire. This one's a little bit harder. In fact, sometimes to do this, it ends up being a little bit easier to use like a physical manipulative here to visualize it. Okay? This is my wire with the electrons moving through it. Okay? You can see on the meter stick an arrow showing the direction of motion of the electrons. We know we're going to use which hand here? Left, right hand? Which one is it? Left hand, because it's electrons, right? The left hand rule, the left hand wire grasp rule. So we're going to say left thumb in the direction of the particles, which is to the right. So stick your thumb to the right. Now, where do you put your fingers? Doesn't matter. How much do you bend them? Doesn't matter. Okay, let's try it like this. Where are my fingers right now? Like, this is my page, right? Right here is my page. Where are my fingers right now relative to the wire on this page? Don't tell me which way they're pointing. Tell me where they are. Look at my fingertips. Where are they relative to the wire? They're pointing upwards, yeah, but where are they? Yeah. They're in front of it, right? If this is your page and this is your wire, then my fingers are in front of that wire, and they're pointing which way, Ryan? Upwards. Right. So in front of the wire, they're pointing upwards. I'm going to indicate that by just an arrow pointing upwards like this. Now, where are my fingers right now? Where are they? Maddie, where are my fingers right now? They're below the wire. And which way are they pointing right now when they're below the wire? Right. So I'm going to say that below the wire, the magnetic field is out of the page. Okay, all of these blue directions indicate magnetic field in this question, okay? Where are my fingers right now? My fingertips, that is. Like, forget about my knuckles and whatever. My fingertips are where? Nathan, where are they right now? Above the wire, on top of the wire? Yeah, which way are they pointing? Yeah, into the page. This is the page, so my fingers are pointing towards the page or into the page. So we're going to say above it. We're going to represent that by an X, because X means into the page. Now, this is where it gets a little bit awkward with your hand. This is where sometimes you got to just turn the body a little bit. Right? You start twisting around like this, and it gets, for old men like me, it gets hard to start moving the shoulders and wrists like that. Twist your body, turn your body around a little bit. Right now, my fingers are where? Bruce, where are they? They're behind. In which way are they pointing? Zane's got. I was just about to call Zane, but he's got a mouthful there. Quinnen, which way are they pointing right now? They're pointing down. So I'm going to draw that like this. Do you guys see the symbol there, what that means? Okay, if you wanted to label that in words, that would be okay. You could say in front, it's pointing up. You could say in back, it's pointing down. You could say above, it's pointing into the page, and below, it's pointing out of the page. Okay, whatever works for you there. Okay, but if you want to just use symbols like this, then absolutely. Just recognize the difference between this one and this one. Make sense? And, of course, these two as well. Good? All right, you had a few questions that you were working on, well, on Friday, and then over the weekend it was worksheet number 10. Worksheet number 10, and I believe there was 5 questions on that worksheet. Let's take a look at that now. We'll go through all of these, okay, from start to finish. So I won't even ask you which ones you want to go over. I choose to go over all of them here. Number 1, fairly straightforward, number 1. Draw the magnetic field surrounding the wire showing electron current below. Electron current. I'm circling that to remind me that it's negative particles. And if it's negative particles, I'm going to use which hand? Which hand, Harrison? Left hand. So I'm going to write a little note there to remind me that it's going to be the left hand. Good. We know it's going to be a circle, right? Or it's actually going to be a bunch of circles. I'll just draw one, though, because we're just trying to find the direction here. Thumb in the direction of the particle, left thumb, direction of the particle. Fingers get clenched. Which way are they pointing here, clockwise or counterclockwise? Shouldn't? Yeah, it's going to be counterclockwise. Good. If you wanted to just indicate that in words, counterclockwise, CCW, that would be okay as well. Magnetic field surrounding the wire, showing electron current below. Like, once again, electron current, negative particles. Left thumb in the direction of the particle, which is out of the page. Fingers go which way? Maddie? Okay. Which way is it? Thumb in the direction of the particle. Fingers are going to point which way? Clockwise or counterclockwise? Going to be clockwise. Good. So thumb, fingers. It doesn't matter where I put them, right? With the way that I had it oriented right here, my fingers were above the wire. But if I had to put my fingers right here, they'd still be pointing clockwise. 3 is when it gets a little bit tougher. This is the example that we just did, right? Electron current pointing to the right. So we'd say here, above the wire, my fingers would point into the page. Below the wire, my fingers point out of the page. Behind the wire, now I'm using my pen as my manipulative, right? Behind the wire, my fingers point which way? Down. And in front of the wire, my fingers point which way? Or up. Yeah, towards the top of the page, like this. For a similar, but not exactly the same question, this time we have, what, an alpha particle, I think? Yeah. An alpha particle, and it's going up the page. This is my right hand, right? Because it's a positive particle. Here's my wire again, or movement of my particle. Right thumb in the direction of the particle. Where are my fingers right now? Maddie, where are they right now? In front, and which way are they pointing? To the right. Good. So we're going to say my magnetic field here points to the right. Where are they right now? Where are they right now? To the right. Which way are they pointing? Good. To the right, and they're pointing into the page. Right now they are, Logan, where are they right now? They're pointing to the left, but where are they? My fingertips? This. Yeah, but they're behind the wire, right? See, there's the wire. Look, there's the wire. My fingertips are behind it, right? Does that make sense? Yes? Yes is slightly better than sure. You sure? Okay. So they're pointing which way? It would be to the left then, right? And then what about this? Zane, now I'll ask you, because I've been looking at you like for the past 12 questions, and your mouth's been full every time. But this time your mouth is empty here. Good. On the left, pointing out of the page. At least you're already there. That's perfect. Okay, on the left, pointing out of the page. Good. Now you can have something to eat again, Zane. Clearly you're hungry, so. Number 5. The diagram below shows magnetic field surrounding a moving electron. Oh, this one's different. We have the magnetic field this time. Huh, interesting. It's a circle, which of course it's a circle. This means it's going to be either into the page or out of the page. Left hand. This is kind of like algebra. Kind of like saying, 3x plus 5 is equal to 7, solve for x. You're rearranging in a sense, except you're rearranging a hand rule instead of rearranging an equation. Usually we say thumb points a certain way, fingers point a certain way. Which way do my fingers point? This time it's, we know which way my fingers point. Let's see which way my thumb points. So fingers go clockwise like this. Thumb is automatically going to point which way? Out of the page. So we'd represent that by a dot. Now, if that confuses you at all, let's say you had to guess on this. Okay, well, no, wait a second. If I'm doing that, my fingers are pointing the wrong way, right? There's no real guessing involved in this, right? Just keep moving your hand around until your fingers are going clockwise, and then your thumb, as long as you got your thumb at 90 degrees here, has to be pointing out of the page. It has to be. And 6, this is an alpha particle. It's going to be a right-hand problem. Thumb in the direction of the particle. We don't know which way the particle's going. So let's do a little algebra on the hand rule. Let's make my right fingers go clockwise. My thumb will point automatically which way? My thumb will point automatically which way? Ben, thumb is pointing into the page. Good. So we'd say this time that my current or my moving alpha particle would be into the page. Right? It's not so bad, is it? No? Soon we're going to have another hand rule that we have to deal with. We won't use it. The good news is we won't use it in this situation. Okay, we'll use it in a different situation. The bad news is sometimes people get the situations mixed up. But if you're clear on this, Okay, if you're clear with how to do this, you should be okay. If you're not clear on how to do this, then you need a little bit more work, or you need to ask me a question to clarify it a little bit. All right. Here's another rule, the second of 3 rules. This one we call the Coil Rule, or at least I call it the Coil Rule for solenoids. Let me define this first. Again, fancy word in physics because, I don't know, we want to sound smart or something like that. Last class, we were analyzing, Physics 20, we were analyzing today problems like this. Problems on, what would you call this? Yeah, well, like normal people would call it problems on a hill, but in physics we call it problems on an inclined plane. Okay, I don't know why. I do think sometimes it's because we want to sound smart or something stupid like that. What's a solenoid? Oh, it's a fancy word for a coil of wire. It's too bad we have to have these fancy words, but we do. Now, if I take a core, and this core is ferromagnetic, and I wrap wire around this core, I think it was Blake that was on the first day of this unit talking about how we apply an electric current, we can generate a magnetic field. You know, we're going to start talking about that a little bit here. In terms of what that magnetic field in that ferromagnetic material is going to look like, how we generate a magnet here. If we wrap wire around it and then apply an electric current through the wire, that electric current will generate a magnetic field. But because it's wrapped around, it's kind of neat the pattern that ends up being produced. If you have, let me take a piece of paper and roll it up here. If you have a coil of wire like this, and you have a wire in the front, one little loop of the wire in the front going up like this, it generates a certain magnetic field. But then going down on the back, it generates inside the coil the same magnetic field. So what you end up having here is a loop of wire that generates a magnetic field in a certain direction, and then another loop of wire that generates a magnetic field in the same direction, and then another one that generates a magnetic field in the same direction. So what do you end up with here? Not just a little magnetic field caused by one wire, but you end up with a big magnetic field caused by this loop of wire, and this loop of wire, and this loop of wire, and so on. It's essentially constructively interfering to produce a stronger magnetic field. Itty-bitty magnetic field combined with an itty-bitty magnetic field combined with an itty-bitty magnetic field makes, in the end, eventually, a pretty big magnetic field. Now, how do we find what the magnetic field looks like here, what the polarity of this looks like? Because it does develop a polarity. A north pole and a south pole ends up becoming a magnet. We're going to use what we call the Coil Rule for solenoids, which is exactly opposite to the rule we just learned. The rule we just learned said, stick your thumb in the direction of the moving charge, your bent fingers, bent fingertips will point in the direction of the magnetic field. This time we're going to say, my thumb points in the direction of the magnetic field, and my bent fingers will point in the direction of the moving charge. So exactly the opposite. Now, what is that going to look like? Let me draw a picture here on the next page. Here's my core. Here's my ferromagnetic material, just a piece of steel, a piece of iron, whatever it is that you're wrapping wire around. Now, my wire being wrapped around looks like this. Do you see what I'm doing there? The wire is going in front of the core as it goes up there, and then it's looping around behind, and then it's looping around in the front again. Do you see what I've done there with my diagram? Does that make sense? And it ends up coming down in the back like this. We got a battery attached there. This battery, by the way, has 2 poles to it, a positive pole and a negative pole. Always remember that the short end of the stick here is your negative terminal, and the long one is the positive terminal. Here's how I remember that. Here's how I personally remember that. Here's the symbol for negative. Here's a symbol for positive. the symbol for positive has the vertical line in it. The longer vertical line is the one with the vertical line in the symbol. Make sense? So negative and positive. That means electrons are going to start flowing away from the negative. They're going to go up in the front, and then they're going to loop around and go down in the back to the start here. Like, we haven't done anything magnetic here so far with this, right? We've just looked at electrically what happens to it. Now, magnetically, what happens? Remember the coil rule. It said thumb in the direction of the magnetic field, fingers in the direction of the current, or the moving charges. Here's what I would like you to do right now. This is the unit of manipulatives. I would like you to make a manipulative right now. I want you to take a piece of paper. I got lots of scrap paper if you don't want to waste one of your precious lined pieces of paper. Lots of scrap paper here. Feel free to take one. I'll start a pile over here and start a pile over here as well. Or if you want to use a piece of lined paper, that's okay. Once you have your sheet of paper, I'd like you to take one or two little pieces of tape as well. One or two little pieces of tape like this, and then I want you to roll up your piece of paper to look something like this. And then tape it so that you've got a coil, or as we call it in physics, a solenoid. Now what I want you to do is on one side of your little roll, or what is for us now a coil of wire or a solenoid, I want you to take a pen or a marker or a pencil or something, and I want you to write the word, this seems silly, but I want you to write the word front. I want you to write the word front. Okay, it seems silly, but I'm telling you, some of you are going to get mixed up between the front and the back if you don't label it with front. If you want to label the other side back, go ahead. But it's important that you at least label one of them. Now, with the solenoid that you just made, I want you to use the coil rule to determine the direction of the magnetic field, or the polarity of this coil of wire. Here's how it goes. Okay, remember, the coil rule is opposite to the wire grasp rule. So instead of saying thumb chart direction of the charge, fingers magnetic field, we're going to say fingers moving charge and thumb in the direction of the magnetic field. Right now, when you look at this diagram on the board here, in front of this coil, in the very front of this coil, which way is the current going? Which way are the electric charges going? Up or down? Up. So here's what I want you to do right now. I want you to take your left hand, and it's almost always going to be your left hand here because we're talking about electric current, and that's what moves within wires, right, is negative particles. But I will tell you an exception to that in a little while. But for now, just stick with negative. Stick with left hand. I want you to stick your left fingers, put your left fingertips on the word front. Say, put your left fingertips pointing up on the word front. Make sense? That's why we have the word front written on it, okay? Put your left fingertips pointing upwards and make sure they're on the word front, just like this. So you can turn it around any way you want, but the bottom line is my fingertips are pointing up in the front, just like you can see right here in this diagram on the board. Current is going up in the front. My fingertips are pointing up in the front. Got it? Which way is my thumb automatically pointing here? Which way is my thumb automatically pointing here? Make sure your thumb's at right angles, by the way. Don't do this. Like, don't join your thumb to your fingers. Okay, your thumb has to be 90 degrees here. So if my fingers are pointing up in the front, my thumb has to be pointing which way? Guys, look at the word front. Okay, do this so you can see the word front. Can you see the word front? On yours, not on mine, on yours. You want to see the word front on yours. Put your fingertips on the word front, pointing up, so that you can see your fingertips pointing up on the front. Bend your fingers around. Now your thumb might be in the back, it might be above, whatever. Bottom line is, which way is my thumb pointing? Pointing to the right.
Oh, I see.
Yeah, that's why you got to look at the word front, right? That's why you labeled it with the word front. Make sense? So that means that the magnetic field, now listen carefully because this is a little bit tricky. That means that the magnetic field inside this coil points to the right. If inside the coil it points to the right, this would be a south pole and this would be a north pole. Because remember, outside, the magnetic field goes from north to south. Inside, it goes from south to north. So we've just established the polarity of this coil simply by sticking our fingers on the word front, looking at the word front, and recognizing that our thumb points to the right, inside the coil. Remember we said at the beginning of the unit, magnetic field points from north to south, but inside it points from south to north. Almost always we're looking at outside. This is the exception to that. This is when we need to look at inside. Okay, let's do another example here, because I don't think you're quite there yet. Here, let's try this one. That's okay. Sometimes this takes a while, and that's okay. Here's another coil, or here's another core, piece of steel, piece of iron, something that's ferromagnetic. Let's stick a wire up like this. Do you see the difference with this one? See the difference with this one? Like the wire's going the opposite way around, right? It's in behind over here instead of in front over here. This is my negative, this is my positive terminal again. That means my current is going up like this, up in the back, down in the front, loops around, up in the back, down in the front, and so on, loops around back to the battery or the power supply, right? Now, you want to find the polarity of this? You could probably guess based on the diagram you see on the left side of the board right now, but we don't want to guess because on a test, you don't have that other diagram there. Everybody take your manipulative. Look at the word front. If you can't see the word front, you've got to point to the wrong way. Look at the word front. Then I want you to take your left hand, and I want you to take your left, specifically your left fingertips, and I want them to point down while they touch the word front. So left fingertips down on the word front, and then bend your hand around. Which way is my thumb pointing? Martin, which way is my thumb pointing? It's pointing to the left. See that? So we're going to say inside this coil, my magnetic field goes to the left, which means, what's the polarity that's going to be? Logan, what's the polarity going to be? This end's going to be what? Yeah, because the magnetic field inside goes from south to north, and then outside, of course, it goes the other way around from north to south. How about this time we have a core like this? How about this time the wire goes around like this? Hey, which one's positive, which one's negative? Top side of this battery, is that positive or negative? Positive, the bottom side is negative, so the current goes from negative around this way. It goes to the right and behind, and then loops around to the left, like this. So it ends up going counterclockwise. Nothing magnetic yet. This is all electrical, right? Now let's do the magnetic part of it. You need to orient your solenoid so that it's vertical this time. So you can see the word front. It doesn't matter whether it looks like this or like this, but you need to be looking at the word front. Staring at the word front. Now I'm not, right? Because I'm demonstrating it from your perspective. You need to look at the word front on mine and the word front on yours. And your fingers need to point in the front to the left. So my fingertips right now are touching the word front, and they're pointing to the left. Get it? Now I bend my hand around. Which way does my thumb automatically point? What? Points up. So that means the magnetic field inside this coil points upwards. Which means that, Dryden, which end is north, which end is south? Bottom or top here?
North is the bottom.
North is the bottom? Agree with that, Blake? I'm going to say south is the bottom, actually. Because the magnetic field Remember, magnetic field outside of a magnet, Dryden, goes from north to south, but inside it goes from south to north. Yeah. Let's try one more. I don't want to say simple, because none of these are simple, but one more rather straightforward one, and then we'll deal with one that's a little bit more challenging here, okay? Let's try, say this time we got something like this. What's this, positive or negative? Negative. Electrons go which way, clockwise or counterclockwise? They're going to go counterclockwise, right? Away from the negative, back towards the positive. So to the left and the back, and a loop around like this, right? That means that my fingertips on the word front are going to point to the right. Bend my hand around, my thumb automatically points which way? Kira? Thumb points downward. Magnetic field is inside towards the bottom, which means, Dryden, this is what pole? This is the North Pole, this is the South Pole. Magnetic field goes from north to south outside of a magnet, but it goes from south to north inside of a magnet. If we want to draw it around like this to illustrate the north to south outside, we can, but it's not necessary either. Now we're going to do one backwards. There's a battery right here. But I'm not telling you what the battery looks like. It's got two poles, a positive and negative. All I'm going to tell you is that this end is south and this end is north. I want to know what the battery looks like. So which way does the current flow, clockwise or counterclockwise, and then based on that, what does the battery look like? Which end is positive, which end is negative? Usually for these questions we say, well, stick your fingers in the direction of the current, the moving charges. Touch the word front, right? And see, and point them up or down. But this time we don't know which way the current goes. We do know which way the field goes. Inside the coil at Dryden, which way does it go? From north to south or south to north? Good. So inside, the magnetic field goes this way. So I'm going to stick my left thumb to the right. Agree? Left thumb goes to the right. And then my fingers, I want to loop them around so that they touch the word front. Which way are they pointing on the word front? Which way are they pointing on the word front, Brendan? Up. Up in the front. So I would say my current would go up in the front, right? And then down in the back. It would go around like this. So tell me, should this be the short one or the long one right here on this side? Short one negative, and this one should be the long one positive, because we go away from the negative and back toward the positive. Is it kind of making some sense? So we got two rules now. We got the wire grasp rule, which says thumb, current, fingers, field, and we've got the coil rule, which says fingers, current, thumb, field. Neither one are crazy hard, but once we start dealing with both of them, sometimes we end up getting them mixed up. Okay? Just logically think through, remember which rule is which, and then logically think through what you've got in each case. What do you see up on the board right now? What is this? It's a speaker, yeah. It's a speaker. And this speaker converts electrical energy to sound energy. Okay, when you attach a wire from your iPhone to your speaker, or even via Bluetooth, the Bluetooth just involves a little bit more electronics, that's all. Okay, a radio receiver basically in the speaker. But in the end, it takes an electrical signal through wires, and then that electrical signal goes around this coil, or what do we call a coil again? What's another word for it? Solenoid. A solenoid. Okay, around this coil or this solenoid, and generates a magnetic field. And we could predict the direction of that magnetic field using the coil rule, right? generates a magnetic field. Now, that magnetic field will change. It will change because the current changes. The current that we see going through there is related to the music signal. The music signal, the audio, gets converted to an electrical signal, which, because the music is changing, the electrical signal changes. Now, as the electrical signal changes around this solenoid, so does the magnetic field that it generates. That magnetic field that's changing, that's been generated by this current, that's been generated by the sound, causes this permanent magnet here to either attract or repel. So this permanent magnet goes back and forth depending upon the electrical signal going through this solenoid. Does that make sense? You're generating a magnet here in this solenoid. It's becoming a magnet, and that electromagnet in this solenoid is causing the permanent magnet to move as a result of attraction repulsion. Now, this permanent magnet is attached to this cone right here. And that cone is basically like, well, depends upon how good your speaker is, but it could be like literally cardboard, or it could be some kind of fabric. This fabric or cardboard that's attached to the permanent magnet goes back and forth with the permanent magnet. So what? Well, what is sound? What is sound? Think back to Physics 20. What is sound? It's areas of high pressure and low pressure in the air, right? If I take this cardboard or this fabric cone and I make it go back and forth quick, I create high pressure areas and low pressure areas in the air, which causes my eardrum to go back and forth. So ultimately, I have sound in my phone converted to an electrical signal that's proportional to the sound, producing a magnetic field that's proportional to the sound, or proportional to the electrical signal, which is proportional to the sound, which causes a permanent magnet to be attracted and or repelled. The movement of the magnet is proportional to the magnetic field, which is proportional to the current, which is proportional to the original sound, which causes a cone to vibrate back and forth, proportional to the movement of the magnet, proportional to the magnetic field, proportional to the electric current, which is proportional to the original sound, which causes my eardrum to vibrate back and forth, which is ultimately proportional to the original sound. Does that make sense? So you get sound converted to electricity, converted to magnetism, causing this permanent magnet to go back and forth, which causes the cone to go back and forth, which produces sound and causes my eardrum to go back and forth. So I hear what was originally produced in the phone. All right? Make sense? What does this look like? Looks like what? Yeah, it looks like a bell, like a fire bell, or it could be an old-fashioned doorbell. I remember when I was a kid, one of my friends used to have this doorbell. It wasn't a ding-dong doorbell like most are, but rather it was a press the switch, and it would just ring as long as you held the switch. But if you take your finger off the switch, it would stop ringing. But even when I was a kid, that was an old doorbell, even when I was a kid. This is more like a fire alarm now, right, or some kind of alarm. What's going on here? Well, you can see a switch here that completes a circuit. Okay, when I press a switch, or when, I don't know, heat or smoke causes the switch to flip. Okay, the circuit is completed. This is the negative end of my battery. This is the positive end of the battery. So that means that I have electrons flowing around like this. They flow through this thing called a make or break contact. I don't know how well you can see this from where you are, but this make or break contact is touching a piece of metal right here. The contact is made right now. So the electrons go through here, around here. They go around here, and then around these loops here. What do those loops do? As the electric current goes through those loops, what do? Yeah, they make a magnetic field. And that magnetic field attracts this piece of steel here. This piece of steel is attached to a hammer. What happens to the hammer as this piece of steel is attracted to these two, well, what we now call electromagnets? They were just solenoids, but now they're electromagnets with electrons going through them. What happens to the hammer? It comes and hits the bell. What do we hear? Ding. Yeah, that's it. That's it. That's all we hear is ding. The electrons, by the way, continue to go around here. Okay, go around here, whatever. We hear a ding. But as soon as that ding happens, as soon as that hammer hits the bell, what happens over here? Exactly. The make or break contact follows the bar, and now contact is broken. So this was my make or break contact right here, and now this would be where the other piece of it would be. Contact would be broken. What happens if the contact is broken? The circuit is cut. The electrons don't flow through here anymore, right? They can't flow through here. So now we have no electrons flowing through the wire. We still have wire, but there's no electrons flowing through them. So those coils are no longer electromagnets. They no longer attract this hammer. So the hammer goes back to where it was. Makes contact. Now what happens? Circuit is complete. Electrons flow around. What do we hear? Ding. Circuit is broken. Hammer goes back. Circuit is complete. Electrons flow. Electromagnets attract it. What do we hear? Ding. Now, if it happens this slow, it doesn't make for a very good alarm. But if we have this happening 50, 60 times per second, then we don't just hear ding, and then 8 seconds later, ding. We hear ding, 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 50 or 60 times per second. Make sense? That's a little bit more of an alarm, right? And that's what we often hear with like a fire alarm. We hear that ding, 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 ding sound. Okay? Or my friend's doorbell when I was a kid. Not Derek, by the way, another one. Okay? One that never hurt me. Good? All right, guys, I'm going to give you a few minutes to work on some questions on page 592. The questions that I want you to work on are questions number 2, 5 to 8, and 10 to 16. 2, 5 to 8, and 10 to 16, please.